Hello everyone, my name is Sajal Singh and I am from IIT Roorkee second year Data Science and AI department. Today we are going to discuss vector spaces and its application. This might be seems to be a simple topic, but it is a unique and an interesting topic. Let's move to our further slide. What is vector space? Vector space is a system consisting of a set of generalized field of scalars having the same rules for vector addition and a scalar multiplication as a physical vector and scalars. In other terms, space that consists of vector together that are associative, commutative, and also follow distributive applications or operations of multiplication of vectors by scalar are known as vector space. For example, let V be non-empty sets of objects on which the operations of addition and multiplication will be defined by a scalar. If the following axioms are satisfied by all the objects for U, V, and W in V, all scalars K1 and K2, then V is called a vector space and object in V are called vectors. So there are given the conditions for a vector space. If U and V are objects in V, then U plus V is in V. Also, U plus V should be equal to V plus U if it is a vector space. That is, vector spaces follow commutative property. If U plus V plus W are solved, that is, V plus W first add and then it is added to U, it should be equal to U plus V firstly added. Then when it is added to W, they should be equal. This is also known as associative property as clearly seen in the third point. Also, if there is an object in that is 0 in V, that will be called zero vector for V, such that 0 plus U is equal to U plus 0, which is equal to U for all U in V. Also, it can be used for W, that is 0 plus W, it should be equal to W plus 0, which should be equal to W for all W in V. For each U or for each W in V, there is an object that is minus U or minus W in V, which is called the negative of U and negative of W respectively, such that U plus minus U is equal to minus U plus U, which will be equal to 0, obviously. If K is any scalar and U is any object in V, then KU is in V. So U plus V is equal to KU plus KV, KT into U is equal to KU plus LU, K into LU is equal to KU, and 1U will be equal to U. That's simple basic mathematics. Moving to our further slides, we will discuss what are subspaces. A linear subspace or a vector subspace is a vector space is a subset of some larger vector space. A linear subspace is usually called a subspace. That is, we are taking a very large vector space and we have to study for a small part. So a subspace of a vector space, that is a small part of a vector space, will be defined as a subspace. For example, if W is a set of one or more vectors in a vector space V, then W is a subspace of V if and only if it will follow the conditions. For a subspace for becoming a subspace of a vector space, subspace should be follow some conditions for becoming a subspace of a vector space. If and only if U and V are vectors in a W, then U plus V is also a vector in W. If K is any scalar and U is any vector in a W, then KU is in W. For your clarification, here we have taken W a non-empty subset and U and V are vectors. Moving to our further slides, every vector space V has at least two subspace. For following these conditions, for become W is a subspace of V, every vector space V has at least two subspaces. Zero vector space is a subspace of V also. V is also a subspace of V. For example, subspace of R square, first subspace will be 0, line should be through the origin, so therefore it is R square. And similarly with R cube, 0 will be the subspace, lines should through with the origin, and for R cube, planes through the origin, therefore R cube is a subspace, has a subspace. If W1, W2, and Wn subspace of vector space V, then the intersection of these space subspaces. Intersection means when all the points meet on some single point, then the intersection of this subspace also subspace of V. Then the intersection, the point where all three or all n number of subspaces are meeting, that point also will be the subspace of V, no matter what. For example, let me take W be the set of 2 into 2 symmetric matrix. So we are showing that W is a subspace of vector M 2 into 2 with a standard operation of matrix addition and multiplication. Here we have taken W a subspace of M 2 into 2 matrix. So let we take A transpose, A1 transpose is equal to A1 and A2 transpose equal to A2. So here A1 belongs to W, A2 belongs to W. So A1 plus A2 also belongs to W. Therefore, A1 plus A2 transpose also belong to W, which the step is missing. But and so A1 transpose plus A2 transpose also belong to W. And on further solving, we will get A1 plus A2 also belongs to W. Here Ka whole transpose is equal to Ka transpose, which is equal to Ka. Since we have proved that all the things are equal, therefore equal to each other, therefore not equal to each other, they belongs to W or they belongs to R. W is a subspace of M2 into 2. Moving to a further slide, we are going to discuss how to make a graph for a subspace. This was taught in our class, one of our lecture. So here we can see which is a subspace, the thing which passes to the origin. You can see that the black line is passing through the origin and is subspace for R square. It will be counted as a subspace. But the blue line, which is not through the origin and going from one axis to another axis or one axis to another axis, is not a subspace. Further, we are going to study what is span. So if you heard the word span, what first thing comes to your mind? I want to know it in comments. The set of all the vectors for linear algebra, what is span? The set of all the vectors that are linearly combined in the vector in the set S is equal to V1, V2, or V is called a span for S. If S is equal to S is set of V, then in a vector space, the span is a subspace of V. The span is the smallest subspace of V that contains the set S. If S1 and S2 are two sets of vector in V, then span S1 is equal to span S2 if and only if each vector is a S is a line combination of those in S and vice versa. Also, span is denoted by span V1, V2, and Vn. Moving to our next slide, how to check span of V. That's the most important thing for us checking a span. We should first choose an arbitrary vector A, B, or any component in V. Here we have taken V, express V as a linear combination of V1, V2, and V. What is a linear combination? When B or any vector should be equal to K1 V1 plus K2 V2 or K3 V3 and so on till Kr Vr. If the system of the equation in above equation is consistent for all choices of V, then vector V1, V2 until Vr spans V. If it is inconsistent for some choices of V, vector do not span V. Here you can see that which is justifying span and which is not. Moving to our next slide, we are going to see what are bases. Definition. The simple definition of is the set of vector S, V1, V2, Vn, subset V in a vector space. V is called a basis for V if S spans V. Here we study what is span, how to check span for V. Next, S spans V. S is linearly independent. S should be linear, and S if it follows both the condition, it will be called the basis of V. Phi. Here we are missing the symbol, but phi is a basis for 0. The standard basis for R cube for ijk is 100. I is equal to 100, j is equal to 010, and k is equal to 001. That is also diagrammatic. Here you can see the diagram of bases, and we can show you that the arrows which are shown in the figure are defining bases. Moving to the next slide, what are the standard bases for R square? E1, E2, En. For R square, E1 should be equal to 100 and so on. E2 should be equal to, this is not for R square, sorry. This is for Rn. Matlab Rn. So E1 should be equal to 10 till 0, E2 should be equal to 01 till 0, and En, which is the last integer, should be equal to 00000, so on till 1. The standard example for R4. Let me take the example R4. Here the first component will be 1 and rest 0. For the next 0100, 0010, and 0010. Usually it is also can be called diagonal matrix in the matrix form. The standard basis for M into N matrix space is shown in the example. The standard basis for Pn you can see easily. You can combine when you will combine this matrix, you will easily see that what I am trying to explain. Moving to the further slide, we are here to conclude with a small topic that is dimension. Here, the definition for dimension of a finite dimension vector space is defined to be the number of vectors in a basis for V. Simple, easily, how many vectors are in the basis of for V are also called dimension. S is a basis of for V a vector space. Dimension of vector space V is denoted by dimension of vector space. So here we are concluding our presentation with explaining what are the basic concepts for vector spaces. Hope you enjoyed it and understood the most important concepts. Thank you for giving your time and watching this video.